All right. So in this video, what we're going to do is talk a bit more about the cumulative hierarchy. So cumulative hierarchy. So we defined this, I guess, formally last time. So just again, give a reminder. We're going to prove some of its properties, some properties about it in this video. But what's the deal? Well, this is defined by recursion on the ordinals. So for some alpha, which is an ordinal. Well, I need to tell you what this definition of the cumulative hierarchy is. The way that we denote the cumulative hierarchy is it's by the stages. So V alpha is supposed to be the alpha-th stage of the cumulative hierarchy. For an ordinal alpha, I need to tell you, well, depending on whether or not alpha is 0, a successor ordinal, or a limit ordinal, I need to tell you kind of what needs to happen. And well, if we have just 0, so if alpha is 0, the definition of V0 is just the empty set. Well, if we take a successor ordinal, so we look at V alpha plus 1, this thing ends up being the power set of the previous stage in our cumulative hierarchy. And well, if alpha is a limit, well, what we do is we take the union of all the previous stages. So if alpha is limit, so if alpha is a limit. So this is the definition of the cumulative hierarchy. These things, again, are called the stages. So these are called the stages. Stages. Did not mean to do that. So these are the stages. Okay. All right. So the cumulative hierarchy ends up being very important in set theory. We'll prove some of its properties in this video, but we'll probably we're going to kind of move on to other things because I really want to talk about like cardinal arithmetic and stuff like that. And maybe kind of later, I think we'll come back and revisit and prove some more advanced properties of the cumulative hierarchy. But so right now we're just thinking about some more elementary properties of these things. So the first one is that all of these guys are transitive. So what's our first kind of proposition? Proposition. Well, for every single ordinal alpha, well, V alpha is transitive. Okay, so how do we prove something like this? The way that we're going to prove anything like this is just by induction. So this is transitive. So what's the proof? So this is going to be by induction. So how does the induction work? Well, we're going to fix some alpha and assume that it's true for everything less than that, and then argue that it's somehow true for alpha. So fix alpha, and assume, well, for all beta less than alpha, that V beta is transitive. Okay, so, well, now what we're going to do is consider the various cases on alpha, right? Alpha is either 0, or it's a successor ordinal, or it's a limit ordinal. We're going to consider those three cases and then argue in each case that it's actually V alpha is actually transitive. So what's case 1? So case 1. Well, if alpha is 0, well, this statement is actually not helpful for us at all, right? Vacuously, it would then be true that for everything less than 0, that thing is transitive. That's just trivia. That's kind of vacuously true because there's nothing less than 0. So what we just need to argue kind of directly is that, well, what we need to argue is that, well, V alpha, which is just V0, which by definition is the empty set, this thing is transitive. So this is true. Why? Well, you could kind of check it directly, or, well, the empty set is the ordinal 0, and ordinals are transitive. So I guess you could think of it like that as well. Okay, so we're good in this case. The next case is, well, what if alpha is equal to beta plus 1? So in other words, it's the successor of some ordinal beta. Well, what do we know since beta is less than alpha? Well, we have by the induction hypothesis that V beta is transitive. V beta is transitive. So we know this is transitive. Well, one of the things that we proved when we talked about transitive sets for the first time, so in a previous video, that if you took the power set of a transitive set, you also got something that was transitive. So by the previous video, so then, or so, the power set of V beta, which is by definition V beta plus 1, which again is V alpha, this thing is transitive. This thing is transitive. And then this would be, say, by a previous video. So by previous video. Okay. And then what's the third case? So, okay, so we're good in this case, right? This is what we wanted to show. And the last thing we need to check is, well, if alpha is a limit ordinal, so case 3. Case 3. Well, if alpha is a limit, well, what do we have then? Well, V alpha by definition is the union of all the V betas less than it. But what are we assuming in our induction hypothesis? We're assuming that all of these V betas, so we can think about this, this is the union of the set V beta, where beta is less than alpha. But what do we know about these things? These are all transitive by the induction hypothesis. And we also proved in that same previous video that if we take the union of a bunch of transitive sets, it's also going to be transitive. So this is transitive. Transitive by the previous video. By the previous video. And the induction hypothesis. But then we're good, right? We just argued that, well, we fixed some ordinal and argued that, well, we assume that it's true for everything less than it. And we argued that it was therefore true for V alpha. So by kind of transfinite induction, it's true for all ordinals. So the conclusion follows. Okay, cool. So that's kind of nice. So what do we know? What do we know about these things? Well, they're all transitive sets, and we actually get something. So the next proposition is kind of kind of another way to describe these things. They're all extending each other. So what's the other result? And from this next result, we kind of maybe have some picture as to there's some picture that set theorists normally have when they think about the cumulative hierarchy, and we'll draw that after we're after we're done. So what's the next proposition? Well, if you have if alpha and beta are both ordinals, and if alpha is less than beta, well then V alpha is a subset of V beta. So this is the thing that we're going to argue next. And this is also going to be by induction, but we want to be we have to be a little bit careful because they're kind of two different things that we could potentially quantify over. We have to be a little bit careful about what our induction, kind of what it is that we're going to be doing induction on. So what's the proof of this? So one way to interpret this is, so note, we want to prove, well, we want to prove for all alpha, for all beta, I guess, assuming that they're ordinals, we want to show that if alpha is less than beta, then V alpha is a subset of V beta, right? This is another way of thinking about our statement. And if we fix beta, so let P beta, let P beta be this statement. For all alpha, if alpha is less than beta, then V alpha is a subset of V beta. Right? Since we're quantifying over the other variable alpha, this is a statement that just has beta as a free variable. And what we're going to do is we're going to do induction on this statement. Because note, if it's the case that for all beta, P of beta holds, well, then we have our proposition. So note. It's enough to show, well, for all beta, P of beta holds. Right? Because then that would just be kind of amounting to flipping the order of the quantifiers here. And how are we going to do this? Well, we're going to do induction on this statement, P of beta. So we proceed by induction. Well, what do we do in a kind of transfinite induction? Well, we fix some beta and assume that it's true for everything less than beta. So fix beta and assume p alpha holds. Well, for all alpha less than beta. And what's our goal? What's our goal? Our goal is to show that p of beta is true. Holds. Okay. Cool. Well, just like before, right? What did we do in this case? We broke it up into the 3 cases. We are going to do the exact same thing. So case 1. What's case 1? Case 1, it's always just showing that it's just true directly for p of 0. So if beta is 0, well, that's just saying we want to show then if something is less than 0. Well, if something's less than 0, though, then kind of vacuously, it's a subset of it, right? Because there's nothing less than 0. So then maybe this statement is true. Maybe, yeah, we can write it like this. You could also do like less than or equal to, right? Because you get the same result. If they're equal to each other, well, then being equals implies that you're a subset of it. So we can maybe write like this. So for all alpha, if alpha is less than beta, then v alpha is a subset of v beta. This thing is true vacuously. Right? But that's what we wanted to show, right? Because that's what p beta would be if beta was 0. Okay, what about the second case? What about case 2? Well, let's assume that beta, say, is equal to alpha plus 1. And so what's our goal? Our goal is, well, for all... actually, maybe not. Let's not use alpha because alpha maybe appears here. What if beta is equal to gamma plus 1? And so what is our goal now? So what's our goal? Our goal is to show that, well, for all alpha less than gamma plus 1, or less than beta, we want to show, I'll write it out, less than gamma plus 1. What we have then is that v alpha is a subset of v gamma plus 1. Right? This is what our goal is. So what we can do is, well, let's fix some alpha less than gamma plus 1. So fix alpha. Well, if it's less than gamma plus 1, it's going to be less than or equal to gamma. And, well, what can we do from here? Well, one thing to maybe note is that, so note that, well, v gamma, that's an element of v gamma plus 1. And why is this true? Well, what is v gamma plus 1? V gamma plus 1, by definition, is the power set of v gamma. But v gamma, some element x, or some set x is always an element of the power set of itself, right? Because it's a subset of itself. So it's in the power set of it. It's in the power set of x. Well, v gamma is a subset of v gamma. So it's an element of the power set of it, which is v gamma plus 1. And so what do we know? Well, we proved in the previous proposition, right, that, well, all these stages of our cumulative hierarchy are transitive. So what we get is that v gamma is a subset of v gamma plus 1. So since v gamma plus 1 is transitive, v gamma is a subset of v gamma plus 1. And so what can we say? Well, then, what do we know about v alpha? V alpha and v gamma are both, v alpha and v gamma are both going to be subsets of each other. Or they're not. Well, v alpha is going to be a subset of v gamma. Why? Well, alpha is also, so note kind of what's happening here. We're using the induction hypothesis. Alpha and gamma are both less than beta. And what are we assuming? We're assuming that, well, for all alpha less than beta, p alpha holds. And what does that statement mean? Well, we're assuming that if we take something, if we take anything that's, so how do I want to say this? I think what's happening here is, well, since we have this relation, what we know in particular is that p gamma is true. And, well, that means that if we take anything less than gamma, it's going to be the case that, say, alpha, it's going to be the case that V alpha is a subset of V gamma. So what needs to be true here is, well, V alpha is a subset of V gamma, right? Because both of these things are less than beta, and we're assuming that this induction hypothesis is holding for everything less than beta. Okay, but what do we know about V gamma? V gamma is a subset of V gamma plus 1 by this statement right here. But, well, that's what we wanted to prove. We just proved that V alpha is a subset of V gamma plus 1, which is equal to V beta, which is what we wanted. Okay, and then what about this third case? Well, this third case is, well, what if beta is a limit ordinal? So beta is limit. What's going to happen here? Well, we're assuming, so we know that for everything less than beta, or any two things less than beta, well, if one is less than the other, then it's going to be a subset of it. So we're assuming for all alpha less than beta, V alpha is true. Well, what's our goal? So fix some alpha less than beta. Well, what do we know? V alpha, that's going to be a subset of the union of all the, maybe I'll do gamma this time, all the gamma less than beta of V gamma. Yeah, I'll write it out like this. Since I'm kind of using, if I want to use this like index notation like this, we'd have to write it like that. Right? Why? Well, alpha is less than beta, so it's going to appear somewhere in this union, but this, by definition, is V beta. So by definition. So then we're good there. But that's what we wanted to prove. So this is good. So the induction goes through. So induction goes through. Right? Well, why? Well, we fixed some beta and assumed that it was true for all alpha less than beta. And, we just argued that it was actually true for beta as well, right? We consider the three different cases. The hardest case is this case 2. This is, I guess, when we're kind of really directly using the induction hypothesis, where we need to use the fact that at this step, because alpha and gamma are both less than beta, it would have to be the case then that V alpha is a subset of V gamma. Okay. But then that's it. So that's what we wanted to argue. Okay, so what just happened? We just argued that, well, if you take any two ordinals where one is less than the other, then that first stage is a subset of the second stage of the cumulative hierarchy. And this maybe kind of justifies a bit of a picture as to what the cumulative hierarchy is kind of looks like. So the way that it tends to be kind of drawn as something like this. Looks like a V. Maybe looks maybe something like this. So here's kind of, this is the idea that, well, we have, we start at the empty set, which is our V0, and we can think about all these horizontal, like we can draw a bunch of horizontal lines here that represent all the different stages of our cumulative hierarchy. So maybe it kind of goes up, and then it kind of goes up like this. Now, the backbone, I guess, of the cumulative hierarchy ends up being the ordinals. So they normally draw this vertical line like this. This is supposed to be the ordinals. And you can kind of justify this. So I think a good exercise, would be to prove, and this would be by induction, well, for all alpha, so for all ordinals alpha, you could prove that, well, alpha is a subset of V alpha. So in other words, like, so maybe V1 is right here, and then, well, V2, and then maybe it goes up, maybe this is V omega. This is going to be the first kind of stage that it's where we're dealing with limit ordinals, and then it's maybe going to keep on going up. Maybe we're at V alpha here, and it kind of goes up forever. And, well, all of the individual ordinals, so like omega, which is, you can maybe think about like right here, that is like first, all of its elements are first appearing at this V omega stage. So we can maybe think about all the individual ordinals as kind of appearing somewhere on this backbone. And we're drawing it as a line, right? Because the ordinals are themselves well ordered. They're linearly, so in particular, they're like some type of linear order. So maybe some other kind of interesting facts is that uh, you need the axiom of regularity for this, but you can prove that every single set appears somewhere in this cumulative hierarchy. So fact um, for each set x, well, what we know is that there is some ordinal alpha. There's some ordinal alpha such that x is an element of v alpha. And you need regularity or foundation. You need foundation to do this. So you need axiom, a foundation to do this. So I'm not going to prove this right now, but because I want to talk about some other things first. But we will come back to actually kind of going through some of the more kind of rigorous development of like this result and some other things related to the cumulative hierarchy. But we'll do that in a bit. And well, because of this fact, the set theorists normally we'd say something like this is the collection of all sets. So V is kind of is because we're using the V's to denote the stages, this, and we're kind of drawing this V here, well, V is normally called the collection of all sets. So V, so for this reason, set theorists denote V as the collection of all sets. Well, and I'm saying collection. I don't think we've actually kind of formally or like actually written down the statement that there is no set of all sets. It kind of has to follow from the fact that there's no set of all ordinals, right? Because, well, there are more sets than there are ordinals. And so if the ordinals don't form a set, there's no way that the set of all sets could be a set either. But I'm kind of and you've maybe heard of like Russell's paradox before, which is kind of very closely related to this. I'm holding off on like writing down that there's no set of sets until there's no set of all sets until we prove that if you take a set and you take its power set, the cardinality of the power set is strictly bigger than the set itself. So we didn't talk about cardinality yet. So you can forget I said anything if you didn't know what that meant. But why am I kind of waiting that long? Well, the argument that you give for that is exactly the same as the argument that you kind of use in Russell's paradox to show that there's no set of all sets. It's actually a specific case of this more general argument involving power sets. Okay. All right. So we'll I guess one thing to mention, and again, we'll kind of talk more about this when we'll kind of revisit all this stuff later. But because of this fact, there's something called the rank of a set, which is kind of like the least stage in the cumulative hierarchy where all of your elements appear. So another fact. There's something called the rank, and so there's something called the rank of a set. And what is it? This is the least alpha, such that alpha is x is a subset of v alpha. And another way to write this is that x is an element of v alpha plus 1. And, well, note, I guess one thing here is note, I know in this case I wrote is an element of v alpha, and in this case I'm writing is a subset of v alpha. I'm doing that on purpose. The reason why is that, well, what we want to say is one reason why we might kind of consider this instead is that one of the consequences of this definition of rank is that the rank of an ordinal ends up being the ordinal itself. Whereas if you kind of let the rank be the least thing such that you're an element of it, you don't get this alignment here with the ordinal, with the rank of an ordinal being itself. And so I guess what we're emphasizing in this case is that the rank of a set is the first stage in which all of your elements appear somewhere in that stage. So for v omega, omega is a subset of v omega, and well, it's the first omega, like the omega stage of the cumulative hierarchy, is the first stage in which all of the natural numbers appear somewhere in that stage. And so that means that the rank of omega is going to be omega. Okay, well, we'll talk more about that. We'll kind of revisit it in some future video. But what we're going to do next is talk about what's called the Mastowski collapse. And then we'll talk about some ordinal arithmetic and multiplication. And then we'll start working on to talking about ordinals. or sorry, not ordinals, cardinals. We're still talking about cardinals.